So number one, a farmer wants to fence in an area of a 1.5 million square feet in a rectangular field. So we start with a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. So we'll divide it in half. There we go. So that's what we're going with. So the dimensions of the rectangle are going to be length and width. I'm going to go with x and y. So call this y, call this x. And once I've established the picture the way I've got it drawn, I've got a parallel fence going here. That gives me a fence here, also y feet long, and a fence here, also y feet long. We have a fence on top, x feet long, and a fence on the bottom, x feet long. So the total amount of fencing in this picture is 2x plus 3y. So I'm going to put F for fencing. The fact that they give me in this problem says the area is 1.5 million square feet. I'm going to go with 1,500,000. Just feel safer with that. So the area of this rectangular space is going to be the length x times the width y. So x times y has to be 1,500,000. So we divide that by x or y, take your pick, I'm going to say divide by x. So I get y in terms of x that way, which is all I really need to do. We're trying to minimize the amount of material, so we're minimizing the fencing. Fencing is 2x plus 3y, too many variables on the right-hand side. By letting y equal something about x, I'm going to get f equals 2x plus 3y. And I'm going to call this 1,500,000 x negative first. So if I multiply the 3 through that, I end up with the fencing required as 2x plus 4,500,000 x negative first. So at this point I got my fencing expression figured out, so I know F prime is going to equal 2 minus 4,500,000 x negative second. We're trying to find the critical numbers of that function. So there are intervals here. X has to be greater than 0, y has to be greater than 0. So it's kind of an interval there. But the fact that neither one can equal 0 means I can legally multiply this by x squared when I have this equal to 0. So I'm going to multiply by x squared here. That gets me 2x squared minus 4,500,000 equals 0. And if the derivative equals 0, that's critical numbers. So I know 2x squared equals 4,500,000, which means x squared equals 2,250,000, half of 4,500,000. So x will equal the square root of that number. And if I punch that in the calculator, it's 1,500 feet. Square root of 225 is 15, the square root of 10,000 is 100, so that's where I came from. So 1,500 feet is what x should equal. Based on my picture, that's the longer dimension there, based on what I've drawn. Maybe y is longer, who knows. But x is 1,500 feet. Y equals 1,500,000 divided by 1,500. So chop a couple zeros. 15,000 by 15 divided by 15 is 1,000 feet. Now I didn't verify that. It does make a minimum. If we test it out, if I pick a number less than 1,500, let's say 0, I get negative, so it's decreasing. If I pick like 3,000 squared is 9 million, double that, subtract 4 million, something, that's positive. So it decreases before it increases to 1,500, so 1,500 does represent a minimum. So x should equal 1,500, y should equal 1,000. Having the dimensions here with the picture on your paper will specifically tell me how to design this. So I don't have to say 1,500 for that side and 1,000 for that. So just having the picture here with the y and x, that'll be sufficient to establish dimensions for the farmer. Problem 2. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for this cheapest such container. First of all, it's an open-top container, so if we take a look at this picture here, the fact that it has an open top means the top doesn't create any surface. So as far as surface area is concerned, we don't care about the top. It says the length of its base is twice the width. So if I let the width be W, the length is twice the width, so 2W. It doesn't give us any rules for the height, so I'm going to assume the height is something different than the width. So I'm going to use a different letter to represent that. They always hold something constant in these problems. In this case, it is to have a volume of 10 cubic meters. So looking at this box, even though there's not a top, the length times the width times the height is the volume. So 2 times W times H should equal 10. And we use that fact to get H in terms of W or W in terms of H. What I told you in class was solving the lower powers easier. So we need H equals 10 divided by 2W squared. 10 divided by 2 is 5, and negative powers are better than positive powers. So H is 5W to the negative second power. And now we have all three dimensions in terms of W, so we're ready to go. So it tells us the base costs $10 per square meter. The base is 2W by W rectangle. So the area of the base is 2W squared square meters. If it costs $10 per square meter, we end up with the cost of the base is going to be 10 times 2W squared, so 20W squared dollars. I'm going to leave the dollar sign off. The sides is just the lateral surface area of this, and lateral surface area of a rectangular solid is the perimeter of the base times the height. In this case, the perimeter of the base is 2W plus W plus 2W plus W, which is 6W. And the height is 5W to the negative second. So the side area is going to equal the product of those, which is 30 W to the negative first power meters squared. And it says material for the sides costs $6 per square meter. So multiply that times $6 per meter squared. Meter squared cancels meter squared. And that gets me the side cost is going to be 180 W to the negative first dollars. Again, I'll leave the dollars off. So the total cost of this entire box is going to be the cost of the base, which is 20W squared, added to this cost of the sides, which is 180W to the negative first. And again, that's my goal in these problems, to create one equation that represents what's going on in terms of one variable. So 20W squared plus 180W to the negative first power. So when I'm trying to optimize cost in terms of a single variable, at this point I'm going to differentiate. Oh, real quick, W must be bigger than 0. H has to be bigger than 0. So again, just there's no really endpoints except for 0 can't happen. So C prime is 40W minus 180W to the negative second power. Again, for the sake of critical numbers, it's undefined at 0, but 0 doesn't count. It's got to be bigger than 0, and then obviously anything that sets it equal to 0. Once again, since W can't be 0, multiplied by W squared is legal. So 40W cubed minus 180 is equal to 0. So 40W cubed is equal to 180 divided by 40. W cubed is equal to 4.5. 180 divided by 40 is 4. All right, so if W cubed is 4.5, W should equal the cube root of 4.5. cube root of 4.5, oops, cube root. Comes out to 1.6510. That'll be meters because that's the unit of length of the property. Now, if I just do a quick verification, if I go from 0 to 1.6510, and then from 1.6510 up to infinity, only one critical number, again 0 can't be the answer. If I put 1 in, I'm going to get 40 minus 180 is negative, so it's decreasing. If I put 2 in, 2 cubed is 8, 8 times 40 is 3, 20 minus 180 is positive, so it's increasing. That verifies, therefore, we're hitting a minimum at that number, and that would minimize our cost. The question is find the cost of materials, so now that we know what W is equal to, I'm just going to replace both of these W's in my cost function with 1.6510, so 20 times 1.6510 squared plus 180 divided by 1.6510. Or you can do times 1.6510 to the negative first. $163.54. All right. Number 3. A Norman window has the shape of a rectangle surmounted by a semicircle. Thus, the diameter of the semicircle is equal to the width of the rectangle. So our Norman window looks like this. Semicircle sitting on top of a rectangle. The radius of the circle going both ways makes a full diameter. So we have a radius here and a radius here, which makes the top half of the rectangle 2r. Therefore, the bottom half is 2r as well. There's no specific relationship between the distance across here versus the height. So I'm going to say h for height. And it gives us the perimeter of the window. So the perimeter would be the sum of the 4 sides. We have the straight up and down side here is h, left and right 2r, up and down h. And then the curved piece here, which is half a circle, is just pi times the radius. It's just the whole circumference 2 pi r, but it's only half of it, so divided by 2. So pi r. So the entire perimeter of this thing is 2h plus 2r plus pi r. For the sake of ease, I'm going to approximate pi. Let's go 4 decimal places. So if I hit the pi button, 3.1415, and I said 3.1416. So 2h plus, this is 3.1416r. If I add that to 2r, I'm going to get 5.1416. What I know about the perimeter of this thing is it's 30 feet, so I can change this p into the number 30. And again, what this allows me to do is to put h in terms of r or r in terms of h. I like h's coefficient better. I'm going to divide, so I'm going to solve for h. So 30 minus 5.1416 r equals 2h. Divide both sides by 2. 30 divided by 2 is 15. 5.1416 is 2.5708. So quick check on that. 5.1416 divided by 2 is, yes. So that's 15. That's going to be 2.5708. R equals h. We're trying to maximize the amount of light, which means we're maximizing area. The area of this is a rectangle. Area of the rectangle is length times width, so 2RH. The area of the semicircle is half a circle, so it's pi r squared divided by 2. And again, I'm using decimals, so I'm going to go ahead and allow that to be a decimal when I get to it. So if I add those two areas up, I'm going to get the total area of the window. So the area of the window is going to be pi divided by 2 is 1.5708 r squared. Pi over 2 is 1.5708. r squared. And then 2rh is going to be plus 2r, but instead of times h, I'm going to multiply by this r expression. So 15 minus 2.5708 r. So little distributed property here is going to get me the area of the window is going to be 1.5708 r squared plus 30r minus 5.1416 r squared. Combine like terms there. We end up with 30r minus 3.5708 r squared for the area of the window. So again, maximize area. We're looking for the maximum area. Area is equal to a single variable r, so we can get what r should equal and then use that to find h. So the a sub w prime is going to be 30 minus, will be 7.1416. R equals 0. R must be positive, H must be positive. We're only working with R right now, so 0 is the minimum. If it equals 0, we get a critical number, so I just got to solve that. So 30 equals 7.1416 R, so R is equal to whatever 30 divided by 7.1416 is. So 4.2007. If I try a number less than 4.2007, let's say 1, 30 minus 7 is point whatever is going to be positive, so it's increasing. If I pick something bigger, let's say 10, 30 minus 71 is negative, so it's decreasing. So it increases and decreases, hits a maximum at that point, and we're trying to find the maximum area. So we want the dimensions of this. So we have a base, we have a height, and we have a radius. So we have 3 dimensions to this normal window. So the base should be double that, so 8.40 if I'm going a couple decimal places. So the base equals 8.40, we're using the unit of feet. The height equals, height is 15 minus 2.5708 r, so if I do 15 minus 2.5708 times 4.2007. It comes out to 4.2008, so 4.20 for the height. And the radius of the semicircular top part is going to be 4.20. So that'd be the dimensions that I need. Number 4. The top and bottom margins of the poster are each 6 centimeters. The side margins are each 4 centimeters. So if we take a look at our poster here, and it says top and bottom margins are 6 centimeters. So up, down 6 centimeters here, up, down 6 centimeters here. The left and right margins and side margins are each 4 centimeters. So I'm going to put 4 centimeters here and here. So this small rectangle here represents the printed material, the big rectangle represents the whole poster. So it says the area of the printed material is fixed at 384. So my recommendation on a problem like this was to let X and Y represent the dimensions, what they're telling us. So the area of this rectangle is X times Y, and it should equal 384 centimeters squared. So if I divide that by X, I get Y in terms of X. The question's asking me to find the area of the poster that's the smallest it can be, so they want the overall poster to be the smallest area possible. The top dimension from here all the way to here is X plus 4, which is a total of X plus 8. And the distance up and down from here to here is just Y plus 6, which is Y plus 12. So the area formula of what I'm trying to minimize, it's the base of the poster, x plus 8 times the height, y plus 12. But instead of y, I'm going to use 384 over x, or 384x negative first. So area equals x plus 8 times 384x negative first plus 12. So now my area is in terms of a single variable. I would multiply that using FOIL first. So first times first gets me 384x to the 0, better known as 384. Outer two terms make plus 12x. Inner terms, 384 times 8 is 3072x negative first. And last times last is going to be 8 times 12 is 96. Got a couple non-x terms there, so add those together, I end up with 480 plus 12x plus 3072x negative first. Again, they gave me the printed area, they're asking for the minimum poster dimensions. The area of the poster needs to be minimized. X must be bigger than negative 8, y must be bigger than negative 12. Obviously they'd be bigger than 0 because of the original dimensions here. So again, just looking at this, I would go with x bigger than 0. So again, we're going to get a critical number here, but set equal to 0. Division by 0 is illegal, but we're not going to be letting 0 be an answer. So if I look at a prime in this case, derivative of 480 is 0, derivative of 12x is 12, derivative of 3072x negative first is negative 3072 to the negative x negative second. So x cannot equal 0, so undefined does not happen in this problem. There are no endpoints except for 0, which again can't happen. So if I just set that equal to 0, I'll find my answers. Since x can't equal 0, I can multiply by x squared legally. So 12x squared minus 3072 is equal to 0. So 12x squared equals 3072. Divide both sides by 12. 3072 divided by 12 comes out to 256. And if x squared equals 256, x can equal plus or minus 16, but again, minus 16 doesn't make any sense in a dimension situation here, so minus 16 doesn't matter. So the only correct answer is 16, probably the right answer. If we do a quick check here, 0 to 16, 16 to infinity. Substituting it in here, in the derivative. If I pick 1 times 12 is 12, minus 3072 is negative, so it's decreasing on that interval. If I pick 15,000, which is in that one, 15,000 squared times 12 minus 3072 is positive, so it's increasing. Don't need a calculator to figure those out. So we're hitting a minimum at 16, which is what we're looking for. So x equals 16 is the magic number for x, 16 centimeters. The magic number for y is 384 divided by x, so if I do 384 divided by 16, I get x is equal to 24 centimeters. The thing to be cautious of in this problem is it asks for the dimensions of the poster. X and y represent the dimensions of the printed area. The poster is x plus 8 by y plus 12. So the poster dimension should be 16 plus 8 is 24. So x plus 8. And then y, 24 plus 12 is 36. So I'm going to say 24 centimeters by 36 centimeters is the right answer. So just be a little cautious there. Much easier to let the x and y represent what you know, but then you still have to modify the answers. So I'd recommend going that route, but don't forget that last little step. Number 5. Rain gutters to be constructed from metal sheet of width 30 centimeters by bending up 1/3 of the sheet on each side to an angle theta. How should theta be chosen so the gutter will carry maximum amount of water? So length of the gutter is irrelevant, and the base of the gutter is what matters for the sake of maximization. There it goes. And it tells us we have 30 centimeters and 1/3 on either side. So 10 centimeters is left in the middle, 10 centimeters is bent up, and 10 centimeters is bent up. It's bent up to an angle of theta, so this is theta here, and this is theta here. And since the top and bottom of this would be parallel to one another, theta is also up here. And it's much more useful to be inside a triangle, so I'm going to put it there. And the shape we're creating here is a trapezoid, so I'm going to have right angles there that I care about. And the area of a trapezoid is 1/2 times the height times the sum of the two bases. So what I know is this is 10 from here to here, so from here to here is also 10. And I don't know the length of this, I'm going to call it x, that's from there to there, and this is the same. And this up and down is the height, I'm going to call it y, and those are the same. So looking at this picture, the area formula for this trapezoid, it's 1/2 times y times 20 plus 2x. Again, it's just 10 plus x plus x, so that's 20 plus 2x. I need to determine stuff about theta, so I need this to be all about theta, and right now it's about x and y. So if I look at the right triangles created here, here's my angle theta up here, my acute angle. Y is opposite the acute angle, x is adjacent, and 10 is the hypotenuse. So I know, using SOHCAHTOA, sine of theta should equal opposite y over hypotenuse 10. Cosine of theta should equal adjacent x over hypotenuse 10. In both cases, if I just cross multiply, I get 1y is equal to 10 sine of theta, and I get 1x is equal to 10 cosine of theta. So now I have the capacity to change x and y into those, all about theta. So area of the trapezoid is 1/2 times 10 sine theta times 20 plus 20 cosine theta. For me, 1/2 of 10 is 5. I'd go there first before I distribute. So the area of this trapezoid is going to be 100 sine theta plus 100 sine theta cosine theta. So now my area formula in terms of the single variable theta that I care about, ready to differentiate and use my critical numbers to find the maximum or minimum. So in this case, we're trying to find the maximum. So A prime is 100 cosine theta. Okay, we have to use the change, or the product rule on the second one. I'm going to let that be function 1, that be function 2. So 1d2 is going to be 100 sine theta times the derivative of cosine, which is negative sine theta. 2d1 is going to be cosine theta times the derivative of 100 sine theta, which is 100 cosine theta. So A prime equals 100 cosine theta minus 100 sine squared theta plus 100 cosine squared theta. As far as endpoints on this one, 0 radians would be flat, so that would make a trapezoid. Pi over 2 radians would be straight up, so that if you make a rectangle at that point, you'd start making it smaller. So if we're trying to find a maximum, the answer's got to be between 0 and pi over 2. So it's kind of like a closed interval problem at this point. So any critical numbers I find between 0 and pi over 2 are the ones that matter. I would punch this in the calculator personally, so I want to set this equal to 0. Bring this over here. So y equals 100 cosine of x minus 100 sine x n parentheses squared plus 100 cosine x n parentheses squared. Clear out everything else is there. Make sure we're in radians, not degrees. Set my window from 0 to pi over 2 on the x-axis. I'm going to go with a 0.25 scale. This makes it easier to guess. And then I'm going to y min max. I want it to equal 0, so negative 5 and 5 is perfectly fine for that. It should intersect somewhere. And I did 0.25, so 0.25, 0.5, 0.751. Between 1 and 1.25, so I'm going to guess about 1.04. But if I do a calc 0 at this point, I'm going to say left bound 1, right bound 1.25, guess 1.05 maybe. It's 1.0472. And our endpoints of 0 and pi over 2 also count as critical numbers, because we do have endpoints in this one. And we're trying to find out the maximum area. So once I get my critical numbers and I've got a closed interval scenario, I go back to my area formula, which is right here. That's not what's typed in my calculator right now. I want to enter those three numbers into my area formula. So I'm done using that, so I'm going to clear that out. I'm going to type in 100 sine of x plus 100 sine x in parentheses cosine x in parentheses. Go to my table and type in 1.0472, 0 and pi over 2. We can see the highest number, 129.9, happens at the critical number, 1.0472. 0 and 100 are less than that. So the maximum volume or the maximum area of the trapezoid is 129.9. So this would be, how should theta be chosen? Theta should be chosen as that. And it doesn't specify radians and degrees. So let's just pretend on the test I'm going to ask for both radians and degrees. So that's 1.0472 radians. That's the right answer. If I change that to degrees, 180 degrees in pi radians. So I just got to multiply by 180 divided by pi. So I'm going to get 1.0472 times 180 divided by pi. 60.00, so 60 degrees would be the degree answer for that one. Got 6 and 7 together because the method is easy. So I'm trying to find the root of this function that's equal to 0. So like we talked about in class, we're going to let x, or y sub 1, sorry, f of x, I'm going to call it y sub 1 is the function we're trying to solve. And equal 0 is required, so if it's equal to 0, you're ready to go. y2 is going to be the derivative of that, so it's going to be 4x cubed plus 1. And we're looking for an answer between 1 and 2, so that kind of dictates what we're going to pick for x sub 1. I like to go in the middle. The only thing that would make this fail is if y2 equals 0 at that number. Well, if I put 1.5 here, it's not going to equal 0, so we should be good to go. That's everything I need in my calculator to use Newton's method. So if I just grab my calculator, I'm going to enter y1 and y2. So y1 is x to the 4th plus x minus 4. I delete all the stuff that's in there though. And 4x to the 3rd plus 1 is y2, the derivative of y1. And I'm going to run the Newton's method program. All we need is y1 and y2, the function we're trying to solve in its derivative, and we need to know where our guess is, which I'm guessing 1.5. And we let the calculator evaluate it down. 1.283781666. It does say correct to 6 decimal places. I'm a little picky on these, so make sure you do round to the right number of decimal places. So x should equal 1.28378. And then the 6 decimal place is a 1 followed by a 6, so we're going to round up to a 2. We look at number 7. This time it doesn't equal 0, so the first thing I want to do is set it equal to 0, so I can either move the 2 minus x over or the 2 cosine of x over. I'm going to move the 2 minus x. So 2 cosine of x, I like to put parentheses just so there's no confusion, minus 2 plus x equals 0. So whatever equals 0 is going to be called y1. And its derivative will be y2. The derivative of 2 cosine of x is negative 2 sine of x. The derivative of 2 is 0. The derivative of x is 1. It does say find all the roots. So this is one where I'd probably want to graph it first. Again, I want to be in radians since I'm doing sine cosine stuff. So I'm going to clear out what's in there. I'm going to type in 2 cosine x in parentheses minus 2 plus x. And negative 2 sine x plus 1. I'm going to turn off the derivative. And usually the answer is between negative 10 and 10, so I'm just going to assume that. So zoom 6 allows me to see that graph. Looks like you got a couple answers there and one more over here. Can't really tell very closely. So I'm going to go from negative 1 to 5 on the x-axis. all the answers seem to be within those numbers. And I'm gonna go -2 to 2 on the y-axis just to kind of shrink it up in there and get a better look at it and see. So it looks like 0, 1, and about 3.7. Those will be my 3 guesses. And I want correct answers to correct to 6 decimal places if rounding is necessary. So once I've established what my guesses are, and again I got y1 and y2 turned on, maybe. There you go. Y1 and y2 are there. You don't actually have to have them turned on, just make sure it's typed in. I've already got the program running, so if I hit enter, it runs again. So I'm going to enter 0 is my guess and 0 is the answer. The next guess is 1, so hit enter again. Ask for another guess, I guess 1. It's 1.109144. And my final guess is 3.7. Hit enter, guess again 3.7. And it's 3.69815367. So 3.698154. And rounding to the final decimal of 6 decimal places. 3 is followed by a 6. 4 is followed by a 1. So our 3 answers are there. Those are all the zeros to the function. Find the critical numbers correct at 3 decimal places of the function, and find the absolute minimum of the function correct to 2 decimal places. So, first off, we're trying to find critical numbers. So first thing I'm going to do is do f prime of x, which is 12x cubed minus 84x squared plus 12x plus 24. There are no endpoints, and polynomial functions cannot be undefined, so only where it equals 0 will be critical numbers. So I'm going to set that equal to 0. And whatever equals 0 is going to be y1. So y1 is going to be 12x cubed minus 84x squared plus 12x plus 24. Y sub 2 will be its derivative, so 36x squared minus 168x plus 12. So I'm going to enter those 2 functions into my calculator. Let's clear out what's already in there. 12x to the third minus 84x squared plus 12x plus 24. And 36x squared minus 168x plus 12. Once again, I don't know what the answers are. Any number that makes this equal to 0 is a critical number, so I'm going to turn that off. I'm going to hit zoom 6, again assuming that all our answers are between -10 and 10. I've got 3 solutions. One's between -1 and 0. One's close to 7. And the other one's, so I'm going to go from -1 up to 8. And I'm going to maybe go from -2 to 2 here. Oops. So I'm going to let x equal -0.5. I'm going to let it be positive 0.6 and 6.8. Guessing numbers near those answers. And again, I've got my Newton's method program already ready to go. So -0.5 leads me to said 3 decimal places, so -0.455. If I try 0.6, I get 0.645. And if I try 6.8, I get 6.810. Now, it does specifically ask for the absolute minimum, so only the absolute minimum matters. So I have a function here. They were looking for a function of value, so I don't have to do any increase and decrease in characters. Just substitute these 3 numbers into the original function. That'll tell me the absolute minimum. So if I go back to y equals, clear out what's there, and we type in the original problem, 3x to the 4th minus 28x to the 3rd plus 6x squared plus 24x. Go to my table, enter my 3 critical numbers, negative 0.455, 0.645, and 6.810. And we're looking for the absolute minimum. Well, negative 1,949 is the smallest out of all those numbers. So, again, as far as the critical numbers to 3 decimal places, there you go. As far as the absolute minimum to 2 decimal places, I'm going to go 6.81 as the x-coordinate to 2 decimal places, negative 1949.07 is the y-coordinate. So look for critical numbers and absolute minimum on that one to make sure you give me all those answers. I'm going to save the other two for another video. I'm out of time.